When we were trying to predict our pie sales based on price, we ran a simple linear regression of the pie sales here in this column on price here in this column, and we had this output over here. And we talked about ways to evaluate the model fit, looking at the distribution of the residuals. But I just want to take a look at a couple of the numbers that are going to be relevant to the topic that we're going to talk about today, which is what changes when you add multiple variables. So for example, here, I see that the R square, which is the the amount of variance in the dependent variable that is explained by the independent variable. So we can interpret this as approximately 20%. So approximately 20% of the changes in pie sales are due to the price. Okay, and we also talked about this particular the ANOVA, which gives us an actual number as to whether this is a significant amount of variance explained. So this is the ratio, this F statistic is the ratio of this mean squared regression divided by the mean squared residual. In this case, we have an F statistic of 3.179, which wound up being significant at the 10% level, but not at the 5% level, which we might want. If we come down here and look at the actual the t statistic for the price variable, we see that its p-value is also the same as that, and there are reasons for that. This is remember that this t statistic is the ratio of the coefficient to the standard error. Okay, and for various reasons I'm not going to get into, there's a reason why in the case of simple linear regression, this p-value and this p-value for the t statistic here and the p-value for the F statistic here are identical. Okay, now notice that if we see that this is not less than 0.05, so we can't say with 95% certainty that this price has a significant effect on the sales, but we can say it with 90% certainty. So notice, for example, we've got the 95% confidence interval here. This is this does include 0, so it goes from on the left here all the way from -53 up to 5, so that includes 0. But the 90% confidence interval, which is here, puts it at -47 to -0.16. So with a 90% confidence interval, we can see that it's still a fairly large interval here, but that it's always negative. Okay, so we might say, okay, well, overall, given this, we're looking at 20% of variance explained. We're looking at not non-significant ANOVA, for the sums of squares, and also a marginally significant t statistic for our only variable. So we might say, well, this is not a really great model. It's okay, but it's not great. So since we have the data, let's go ahead and see if we can improve it. So instead of trying to predict the pie sales just from price, we're going to also use advertising. So this is the price that we're charging, and this is the amount that we're spending on advertising on that particular week. Okay, so this is going to be a multiple regression. That is, we have more than one independent variable. So in the simple case, we just have one, and in the multiple case, we have more than one. So I'm going to just go ahead and do this. We do it exactly the same way. So do data analysis, regression again. Okay, so my dependent variable, once again, will be pie sales, and I'm going to select the label along with it. And now I'm going to go ahead and take this whole, these two columns here, The labels are in the top here, so it knows it's two different variables. Okay, so I'm going to keep the 90% confidence interval in case we in case we don't have a 95% significance level. So, all right, let's go ahead and see what this looks like. Okay, now we're gonna let's go ahead and evaluate this model using the same standards that we used before, just in terms of those measures of model fit. Let me lop off some decimal points here, make it easier to read. Okay, so now we can see that we've got an r square of 0.52. Okay, so just as a reminder, over here we only had 0.19. Okay, so it looks like we're explaining more variance. We're explaining over half of the variance in pie sales with these two variables. Also notice down here, if we look at our F statistic, it is twice as large as our previous one. Okay, so, and the p-value for this is less than 0.05. So we can say, okay, with this model, with two variables, we are explaining a significant amount of the variance in price, in sales. Okay, so now we come down here to each of the variables and look at their hypothesis tests independently. Now notice something interesting here. Well, let's look at advertising first. So we see that the t statistic here is 2.8, which is, so it's got a p-value of less than 0.05. So we can say with 95% or 95% or greater confidence that advertising has a significant effect on sales. Okay, and over here now we have the price, and we can see that this p-value is also less than 0.05. So price also has a significant effect on sales. Okay, now notice something interesting here. So we can say that this is a very solid model, that both variables are significant at less than 0.05, at a p of less than 0.05. But the question that you might be having is, if we just look at the price row here, we had price before, and we had a p-value that was greater than 0.05. So just as a reminder, over here when we did the simple case, we had a coefficient of negative 24.034 and with a p-value of 0.098. Okay, now if we look back over here, the price, we have negative 24.975. Okay, so it's larger, and now its p-value is less than 0.05. Okay, so now you might be asking, well, why did the effect of price on sales change when we added advertising? How is it possible? It would stand to reason that if price affects sales, regardless of what other variables you consider, price would affect sales the same way. Okay, now this is one of the issues that comes up when you're doing multiple regression. Okay, now one of the key additional assumptions of a multiple regression is that we assume that there is no perfect multicollinearity. Okay, so what does that mean? Well, basically, what you can't do a valid multiple regression with variables that are highly correlated with each other. If you have two independent variables that are highly correlated, the regression gets confused as to how much variance to attribute to which variable. So you may have biased coefficients here, biased estimates. Okay, so multicollinearity just means that these these two variables wind up having lines that are very similar to each other. Okay, so let's go ahead and check on this then. Let's look at whether price and advertising are too highly correlated, So the only way that these estimates would have changed is if these two are correlated to some extent. What we want to find is if they are correlated too much. Okay, so let's go ahead and look at the correlation between these. And we could always just use the Excel function, but we have a nifty tool over here under data, our usual data analysis tool pack. And I'm just going to go ahead and select correlation. Okay, and actually, let me get back to the data. Okay, I want to look at this, and I want to see, okay, are price and advertising correlated? Are they highly correlated? So data analysis, correlation, and I'm going to select these like this. Okay. All right, and the labels are in the first row, and I'll just put, just set the output right there, and I'll show you what it makes. Okay, so output range. Let's see if it'll pick it up that time. Okay, let me get this, make sure all these selections are correct here. Okay, there. Okay, so now we've got what's called a correlation matrix here that puts price and advertising together. Actually, sorry to do this again, but let me do this again, but this time I'm going to include all of the variables because that's a useful thing to see. I'm going to look at the relationship among all three variables. Okay, so now we can see, okay, that, okay, so how this works is the variables appear in both the rows and columns, and it tells you what the correlation is with that pair of variables. And of course, along the main diagonal here, you're going to have ones because pi sale, every variable has a correlation with itself of 1. Okay, so what we can see here is that, so we're interested in pi sales, so we would expect that there would be some degree of non-zero correlation between pi sales and each of the independent variables, right? So we'll look at this column and we'll see, okay, well, that's good. Price has a strong negative correlation with pi sales, and advertising has a strong positive correlation with pi sales. Okay, so that's good. So this column will tell us that we should be able to have a multiple regression that has a lot of predictive power to it. But this is the one we want to make sure is okay. So if advertising and price have a large degree of correlation, let's say greater than 0.9, then we want to start to be concerned about whether it would bias our coefficient estimates. So if we look here, we see that pricing and advertising, the correlation is not 0. Okay, they're a little bit correlated. But this is the reality of life. It's very rare that you have two independent variables that have no correlation whatsoever. So we see that this is a correlation, but it's pretty small. And the fact that this is non-zero is what explains this change, this slight change in the coefficient on the price variable. Okay, so what you'll see is as one by one you add independent variables to a model, the existing estimates might change a little bit up and down, but as long as the correlations between those independent variables are not too great, you should be okay, and you should only see a little bit of movement in those. If they suddenly are significant negative and they flip to significant positive, then you probably have a big problem with too much correlation / multicollinearity among your independent variables. Okay. All right, so that's one thing to look for. So we've got our significance here. But now I want to make you aware of, so it's very nice that this R-square went up to 0.521, but when we're dealing with a multiple regression, the R-square that we want to look at is actually this one here, okay? So it's this adjusted R squared. And notice that it is less than R squared. Now why why do we have this adjusted R squared, and what exactly is it? Okay, so just you know, to remind you what we're looking at here, now we have a new equation. So we're estimating sales, and let me just very quickly see if that's the same. Okay, so yeah, it's the same intercept that I have. So it's the basic equation is going to be, you know, the intercept plus each of these variables times the x value for that. Each of those coefficients times the x value of that. So we have 306 minus 24.975 times the price, yep, plus 74.131 in advertising. Okay, so this is our multiple regression equation, and all we have to do is throw in a price and throw in an advertising. Okay, now remember that when we were interpreting these coefficients in the simple linear regression case, we were able to just say that so in the simple linear regression case, we were able to say that, okay, how do we interpret this variable? Well, we say, okay, or since it's negative, we'll include that. For every 1 unit increase in price, so every $1 increase in price, we can expect our sales to go down by, 24, basically 25. Okay, so for a 1 unit increase in price, our sales will go down by 24. Now, in interpreting this in the multiple regression case, we have to add one more phrase, and that's that is holding the other variable constant. Okay, so this change in price here has this effect on sales as long as there is no change also in advertising. Okay, so the correct interpretation is, so over here, for a 1 unit increase in advertising spending, we can expect a 74 unit increase in sales holding price constant. Okay, so that's what these coefficients are. They are the effect of this variable on the dependent variable, assuming no other changes in any other variables. Okay. All right. So now remember that our models are going to look a little bit different now. So in the simple linear regression case, we just had the one independent variable. So that was here. Okay. And we talked about what these look like and why we use Greek letters and how this is errors and so forth. Now, the only difference is, with our model definitions, remember that I stands for the row. Okay. And so we still have these subscripts here. So these x's refer to the x's that belong to that particular row. Okay. So the values of the x variables on that row. And then we've got these parameter estimates here that are coefficients that are multiplied by that you multiply by those x values. And then these particular subscripts here just refer to the number of x variable. Okay, so this is our first x. So in our case, that was price. And then in this case, this is the second x variable, which in our case was the advertising expense. Okay, so other than that, so now notice that there's two subscripts on these x's, and that just means this is the first x and this is the second x. Okay, and then everything else should look the same. And so the single regression model extends quite intuitively to just adding multiple variables. Okay, so that's all we're doing, is we're just adding an additional variable into the mix. Okay, so one example that we talked about where you can see why this would result in better models is rent price here in Radford. We would have some basic intercept, and then we said that the distance to campus would have some impact on the rent price, but the estimation procedure is what would actually give us that effect. And but we could come up with lots of other factors that would affect the rent price. For example, the number of bedrooms. Okay, so number of bedrooms would have an impact, then this particular, this beta 2 here would give us, okay, so if you have if two apartments are the same distance from campus and you added one more bedroom, this would be the change in the rent price. Okay, so that's the interpretation of that variable right there. Okay, now so it's great that we can get these better model fits when we add more variables, but we have to be careful about just looking at r squared, because r squared will never decrease. Even, when we add a new variable, r squared will never decrease. Okay, so it can only make r squared go up or stay the same. Okay, so we could add more and more junk variables on there. We could just add variables all day and then just watch our r squared go up and up, but we're not necessarily looking at a better model because it's a more complex model that needs more data. And what you want to have is the simplest model possible that gives you an acceptable level of prediction accuracy. Okay, so let's think about why it is that r squared will never go down. So I mean, it will always either stay the same or go up. Okay, and let's think about what r squared is and how that would work. So remember that r squared is can be interpreted as the percentage or the proportion of variance explained. I'm not sure what this is or why it's there, but it will not close. Okay. So remember that r squared reports the proportion of total variation in y that's explained by all the x variables taken together. Okay, so this is what's new, all the x variables taken together. So remember that we had this ratio where we had this regression sum of squares to this total sum of squares. Okay, and this total sum of squares was we're adding up all of the different how much variability there was in the dependent variable. Okay, so it was how much did y really vary around its mean. Okay, so this was the total sum of squares, and our regression sum of squares is we were adding up the sum of the square differences between our estimated y, that's our estimated y's, and the mean y. Okay, and so what this total sum of squares would be this plus our error sum of squares, right? So the two different sources of variation would be the variation that we explained here, and then the variation we didn't explain, which was the difference between our the actual y's and then what we estimated the y's to be. So this was our residual, right? So the y sub I minus the estimated y sub the estimated y, and these are the squared differences. So this was the sum of squared error. Okay, so this total would be this plus this. Okay, now so here it is in a more readable format. So we've got our r squared is this right here, this regression sum of squares, okay, over this. Okay, so we want to know how much of the variability have we explained. Okay, now the way ordinary least squares works when it's trying to come up with our parameters is it's trying to minimize the errors, right? So remember we've got these errors over here, and this is what's going to be minimized. It's going to make this as small as it can possibly get. Okay, so if we look back here at this, okay? So the squared errors, so it's going to be minimizing, and then this, so if we take the difference between the actual y value and what we estimated the y value to be, remember that this is actually our regression equation, so we can just substitute in the whole equation for it. Okay, so OLS is going to be trying to make this error as small as it can possibly be, right? And so basically the further off our estimate is, the larger the error is going to be. Now, if we were to add a new variable in here that made it worse, that is, that actually made the prediction further off and made the residual larger. So let's just say we have we have this new variable x2, and we have, our estimate for that coefficient would be this. If this were in here, if we were to add this in here, and it made this get further off, if it made this further from the true y, then OLS would just simply say, okay, set that equal to 0. Okay, so in the worst case, the variable, so in the worst case, r squared stays 0, or r squared stays the same, okay, because that variable would just be zeroed out, okay. And if this variable improves the prediction by even a little bit, even a slight little bit, then OLS will go ahead and keep that variable in there. So it'll make this non-zero, okay? It's only if this variable makes things worse that it's zeroed out. But then if it makes even a slight little bit of improvement, it'll go ahead and give this a non-zero coefficient. And so our r squared will go up, but maybe only by a little bit, okay? So so the upshot of this is, because r squared is this ratio here, SSR will always go up, or usually always go up. At very worst, it won't change because that variable will be zeroed out, and SST will stay the same. Okay, so when we do multiple regression, we have to look at this thing called adjusted r squared. Okay, and I'm going to show you how it's calculated. Well, first let's take a look back at the regression output. Okay, and we have this adjusted r squared right here. Okay, and notice that it is lower than r squared, and we know because this is a multiple regression we need to be looking at this. Okay, so really we're not explaining 52% of the variability in the dependent variable, we are explaining 44%. Okay, now why, what is it about this adjusted r squared that makes it, more accurate than this r squared? Well, we know that r squared is a little bit of a cheat because you can add a bunch of variables, but adjusted r squared penalizes the addition of variables. And let's take a look at exactly how. Okay, so I'm not actually going to ask you to calculate an adjusted r squared, but when you're confronted by an equation like this, it's sometimes helpful to just go through and think about how a change in one variable affects the value of the output. Okay, so let's think about this. So what we have here is we start off with an r squared. Okay, so r squared is actually part of computing adjusted r squared. So we first calculate this. So remember, when we're finding adjusted r squared, we first have to go ahead and take that SSR over SST, and then we start with that. So we have our r squared. Now, if this k refers to the number of variables, okay, so this is our number of variables. Let's say that we have gone from one variable to two variables, and r squared has stayed the same. Okay, So that would mean that coefficient for that new variable has been zeroed out. How does this affect the adjusted R squared? Okay, so if K goes up, right, so that's gone up by 1. This has stayed the same. This goes up by 1, which means this particular, so this expression down here has gone down, right? So that one has gotten smaller. Okay, so that's gotten smaller. And now this, if this has gotten smaller, this entire fraction, so when the denominator gets smaller, this entire thing gets larger, right? So that gets larger, okay? And we're multiplying it by this. So R squared hasn't changed, so it's the same thing we're multiplying before. And that means we are since we're subtracting it from 1, we're subtracting a larger number, okay? So as K goes up, that tends to pull adjusted R squared down, okay? So that's if R squared doesn't change. But what you would hope is if you add another variable, yes, K will go up, but so will R squared, okay? And if R squared goes up, this whole thing goes down, which means you're subtracting a smaller number. So what you want, the adjusted R squared lets you see that, okay, you've added a variable, but did that variable contribute so much that it continued to improve the adjusted R squared? Okay, so it's, yes, K went up, but if R squared went up even more, then your adjusted R squared is going to remain pretty high, okay? Well, so let's take a look at, so our adjusted R squared here, so wound up being 0.442, and we can, let's take a look at what happens when we put in a variable that does not do a very good job of explaining anything. So let's just, I'm going to put in a random number here, okay? So just, it has nothing whatsoever to do with pie sales, and it should not improve the prediction, okay, because it's just a random number. And so in Excel, you can just do rand, and it'll give you a random number, random float, random real number between 0 and 1. Okay, I'll copy that down. Okay, and I want to keep these values consistent, so I'm going to copy and then paste them as values, so it gets rid of the constant recalculation. Okay, yeah, there it goes. So we've got just a random number thrown in here. Let's go ahead and make a new regression that includes this random number. Okay, and then just see what happens. Okay, I don't know completely what's going to happen, so I'm interested in seeing. It would be a surprise if this does help the prediction, but let's see. Okay, so we'll take data analysis. Okay, data analysis, regression. Okay, all right, pie sales is already selected, but now we're going to select all 3 of these variables. Okay. All right. And so now notice what happened. So we added this additional variable that was completely random, and notice what happened with R squared. So it went up to 0.53, and our R squared on our our multiple regression that just included price and advertising, it was only 0.52. So adding that one completely useless variable actually caused R squared to go up just a little bit. But if we look at adjusted R squared, we see that it is only 0.406 as compared to before, which is 0.442. Okay, so we see that we added that variable, r squared went up just a tiny bit, but that additional k, having that additional variable caused adjusted r squared to actually get lower. Okay, so you see how adjusted r squared actually is a better measure of how well your model fits and the amount of variance that all these variables are actually explaining. Okay, so let's go ahead and verify that this is how this is calculated. I'm going to go ahead and put the go ahead and manually calculate r squared on here. Let's see, there's the equation. Okay. Okay, so I'm going to set, just going to call this manual adjusted r squared. Put it right here. Okay, so this is going to be equal to 1 minus, and we'll do a double here, 1 minus, and r squared was here, okay, times, okay, n minus 1. Now, we have our observations here was 15, so I'm just going to put 14, okay, 14 over, and then n was 15, okay, so it's over 15 minus, and there were two variables, right? 15 minus 2 minus 1. Okay. Okay, I've lost track of my parens here, but okay, so there it is. So I've actually manually calculated r squared, adjusted r squared, and verified that that's how that was calculated. So let's see what would happen if we, so if we had exactly the same, so if we had the same r squared, but we had 3 variables in here. So all I would have to do is just change this to 3, and r squared would have gone down to 0.391, and if I added 4, r squared goes down further. Okay, so the more variables you have, if you don't have any change in your r squared, then your adjusted just keeps going down and down and down. Okay, so this gives you that discipline to say, okay, when do I stop adding variables when they don't really, have any kind of significant impact on r squared anymore? And adjusted r squared would tell you that. Okay. All right. So that's really the key difference. So there's 2 key differences when you move from simple linear regression to multiple regression, and that is you interpret the coefficients a little bit differently. You have to add that clause assuming no other change in any other variables or holding other variables constant. And then you really need to be looking at the adjusted r squared rather than the r squared.